Welcome back all of you. In the last lecture we have started off with critical state model, and the first one that we discussed was Cam-Clay model. We know that this is an elastoplastic model which utilize the concept of critical state. We have also seen the yield curve, and we noted that it is a logarithmic spiral. Now, there were some other developments in the critical state model, and that led to modified Cam-Clay. So, in the last lecture we told that there are certain aspects related to plasticity behavior of soil which also need to be incorporated. In the last lecture I purposely did not introduce those, because we first need to understand what a critical state model would look like. We have got a feel of it, we have defined the yield curve, we have defined it mathematically. So, now we are conversant with the whole process. So, in today's lecture we will see the modified Cam-Clay model along with some basic aspects of plastic behavior of the soil. I mean to say mechanical plastic response of the soil. So, today's lecture we will start with modified Cam-Clay model. So, this is what we will be dealing with in today's lecture. In fact, Cam-Clay and modified Cam-Clay model, it was more or less developed during the same period. The initial one was proposed in Schofield and Roth, and later the modified Cam-Clay model was proposed by Roscoe and Berland in 1968. And we know that these models were essentially developed for defining the triaxial loading or the triaxial test. These are popular elastoplastic model that can incorporate hardening, softening that happens during shearing. I mean to say, it is not like elastic response and then failure. After yielding, there is some other response that we have already noticed. It can be either hardening or softening, and when that gets incorporated, we say it is an elastoplastic response. Critical state is the bounding surface. Now, what is so specific about Cam-Clay and modified Cam-Clay is it is entirely based on the critical state concept, and hence the critical state forms the boundary of the soil. It is the bounding surface, and the soil shears under the consideration of ideal plasticity. The parameters of modified Cam-Clay model are obtained from experimental data, and that is the beauty of Cam-Clay models. Rather, we can get the parameters needed in a simplified manner. For example, lambda, it comes from consolidation tests, either it comes from isotropic or one dimensional consolidation. The failure response in terms of M, it comes from triaxial testing. So, there is a way by which you can determine the parameters in a more simplified manner. The major difference between Cam-Clay model and the modified Cam-Clay model is in the shape of yield curve. I think we have discussed this before also. So, the major difference is in terms of the shape of the yield curve. The earlier one we have seen that it is a logarithmic spiral. So, in Cam-Clay model yield curve is logarithmic spiral, whereas in MCCM it is ellipse. Now, ellipse defines a more symmetrical and regular shape. It is not about symmetry, it is about the corners. Like in the logarithmic spiral, we have seen that it comes and meets at a particular point. Now, this may sometimes create issues in numerical instability as you solve the problem, because there is an issue of continuity of differential equation. So, what happens is in the case of modified Cam-Clay, it becomes an ellipse. So, it is a more smooth shape. we can say. It is not about symmetry, it is about more smoothness in the shape. Now, the thing is, the assumed shape may not be truly representative of the observed yield curve. Now, if we actually want to determine the yield curve experimentally, we have seen that it is quite an extensive procedure. You need to find out different ways by which the soil gets yielded, and then you join all those points. It is not that easy. So, that is why the definition of the shape becomes important. Now, what it says is that the shape which has been assumed, which is an ellipse, may not be truly representative of the actual soil behavior. So, it is an idealized condition. The actual behavior may be something else, some other shape, okay, but it is very close to it. A logarithmic spiral or ellipse can be considered close to the realistic yield curve, and it is essentially assumed because of its simplicity in shape in defining the yield curve, and it is close to the isotropic consolidation in the lab, which can be easily captured in this shape. It is found to be applicable for clays and non-clay soils as well, even though there are deviations. For some soils it may not behave properly, but in most of the soils, in the absence of any other model, this is found to be a fair approximation. Now, the beauty of ellipse is the ratio of major to minor axis can be conveniently considered as the shape parameter. Now, when I say ellipse, we also need to know how it changes depending upon the condition. Now, this changes can be incorporated in terms of the shape parameter, and in this case the major and minor axis becomes a very important shape parameter. We will see how. Now, let us start again with this statement. The essential elements needed for any elastoplastic models like CCM or MCCM are elasticity, yield criteria, plastic potential and hardening rule. It is very easy to understand what is elasticity, because that is what we were exposed to most of the time during our undergraduate and in some of the courses that we deal with in the postgraduate as well. So, it is pretty easy, and the parameters are quite simple if we make an extra assumption that it is linear, elastic, isotropic and homogeneous. So, this simplifies a lot of things, and you are left with only two elastic parameters. You can define the elastic response of the soil using two elastic parameters. One is modulus and the other one is Poisson's ratio, and this modulus can be Young's or bulk modulus that we have seen earlier. So, that part is done. Now, for material like soils which exhibit plastic behavior during shearing, we also need to know where it would yield. Now, in this particular course, we have extensively discussed on how soil is going to yield, at what point it would yield, and we have discussed about yield curves, the various aspects related to yield curve. Now, when I say we have extensively discussed, it is still at an introductory level. Please keep this in mind. If you want to know more, you have to read a lot further related to plasticity behavior in geomechanics. So, we have just understood how to learn and where to start with. So, we have discussed to that particular aspect what is yielding and how do we define yield. And later in the last case in CAM-clay model, we have also discussed about how it is going to yield and what is the boundary that we have fixed. So, we have clearly defined at some point the elasticity behavior changes. Now, yielding is not failure when it comes to elastoplastic behavior. Elastic, perfectly plastic, like models like Moore-Coulomb, we have seen that yielding itself is a failure condition. Now, if you want to incorporate hardening, softening condition, this is not possible. So, that is where the elastoplastic models are important. Now, yielding is the point where it undergo transition from elastic to plastic behavior, but that is not failure. The yield curve expands, and how it will expand, that part we do not know. We know that the as the effective stress path go past beyond the yield curve, the yield curve start expanding, and when it meets the critical state line, I mean to say the effective stress path meets the critical state line, that particular yield curve which is at the point of intersection of the effective stress path with the critical state line, that particular yield curve denotes the failure one, beyond which there is no further expansion. Now, how do we explain this many sequence beyond yielding? For that, we need to know about the plastic behavior of the soil as well. This particular aspect we just told in CAM-clay model, but we did not discuss this. Now, putting everything in one shot is going to be difficult for you to understand. So, we did not discuss this intentionally in the last lecture, but at the same time we need to know some basics of what happens to the soil during plastic behavior beyond yielding. So, this is the starting point where you can capitalize further and do further learning. So, this is important. Please understand, whatever we are going to discuss now in terms of the third one, that is the plastic potential and hardening rule, which essentially state the plastic behavior of the soil. This part is the beginning, and this shows you what to learn and from where you have to start related to the plastic behavior of soil. And now you need to build on this for actually implementing this model into practice. So, let us start. Now, yield curve is ellipse in the case of MCCM. We will be discussing everything with respect to MCCM, but that is remaining common for any other plastic behavior as well. So, first of all, elastic behavior of the soil, then the yielding, then the plastic response, then the failure. So, there are 4 stages in which we need to conceive a soil behavior when it is loaded. Any material will exhibit some amount of elastic behavior. Now, it may be at a very small stress range or it may be at a higher stress range depending upon the stiffness of the material. Now, there is a point at which the yielding happens, and that is defined by the yield curve. Up to that, stress strain response can be defined by elastic behavior or elastic models. Then you need to fix a point where it will yield, that is yield criteria. So, that also we have seen to some extent. Now, beyond yielding, it can undergo hardening or softening behavior. Now, there are different models to account for these behavior, and that is included in the elastoplastic models, various types of elastoplastic models. In that, one particular model is CAM-clay model or modified CAM-clay model. Now, how this is going to proceed beyond yield curve, that is defined by plastic potential or hardening rule, that states the stress strain response under plastic condition. So, once the plasticity sets in, how will you define the stress strain behavior of the soil, how it will proceed. So, that is given by this, and finally, the state boundary which is defined by the critical state defines the failure. So, these are the 4 steps in which you need to understand the soil when it is subjected to shearing. So, yield curve is ellipse. Now, for initial isotropic compression, ellipse is centered on P dash axis and it passes through origin. Now, this particular definition is with respect to MCCM, how the ellipse would look like in Q P dash space. So, let us first define in Q P dash space. So, what it tells is, now yielding, as I told, it need not mean failure. It can happen in isotropic compression, it can happen in one dimensional compression, or it can happen in a triaxial loading. So, for initial isotropic compression, ellipse is centered on P dash axis. So, the center of the ellipse is on P dash axis. So, it is on this axis and it passes through origin, the one side of the ellipse it passes through origin. Let us see how. So, this is how we define the ellipse. So, you can see that the center is on the P dash axis and it passes through the origin. So, this is an elliptical yield curve in MCCM. Let us call it as yi, and the yield curve is defined by its P dash y, that is the yield point. So, this also we know, we have already seen this. Now, this on the ICL, NCL, P dash y is transferred to this particular point. Now, we need to see that this is another kind of very important aspect, that the midpoint of the major axis is here. So, this is P dash y by 2, this particular point, and that is the point through which the critical state line goes. And how does that look in Vp dash plot? So, this point, that is the point where the loading, unloading, reloading line passes, or it crisscrosses the critical state. It does not mean that this is meeting, but this is the location. So, up to here what it means is that up to here, this particular point, it is elastic response and then it goes beyond. So, here in particular the elastic response of the soil, and this is the point. So, this is very specific to MCCM model, that is the yield curve. Please note, these are very important aspect which you need to keep in mind, that is when the yield curve touches the critical state line, that corresponds to this loading unloading line which is unloaded from P dash y. Now, P dash y is the extreme point of this ellipse. Now, this is true for any bigger ellipse as the effective stress path moves ahead. Definitely this particular point will be m into P dash y by 2, provided that is the failure point. Now, the stress ratio, that is Q upon P dash, if you call it as eta, Q by P dash, anyway we are going to discuss this later. Q by P dash, if it is eta, Q by P dash is the stress ratio. Now, this eta will be equal to m when the yield is corresponding to the failure condition. Till that it is eta. Now, this let us consider it to be a failure condition. In that case, Q is given by m P dash y by 2, because this is P dash y and the slope of the critical state line is m. So, at this particular point where it touches at the extreme top point of the ellipse, it is m P dash y by 2, and this distance is half of the major axis of the ellipse, which is P dash y by 2. Now, it is very easy, since the elliptical yield curve is defined, we just need to define the equation of the ellipse, and that comes from our basic geometry. Now, equation of ellipse with center at HK. Now, this is the point HK, this is the center. You can write it as x minus h the whole square by a square plus y minus k the whole square by b square, where a and b are half of major and minor axis. So, a is major axis by 2 and b is minor axis by 2, is as per the equation of ellipse, and h and k are the center. Now, here h is for p dash, that is P dash y by 2, and k, it is on the P dash axis, so it will be 0. So, this if you substitute, x means it represents P dash, minus h we have already written P dash y by 2 the whole square divided by a square. Now, a is the total is P dash y, so a will be P dash y by 2 whole square. y is q axis, q minus k is equal to 0 whole square divided by b is given by m p dash y by 2 whole square, which is equal to 1. Now, what we have done is we have incorporated some parameters which will define the yield, and that is in terms yield curve, that is in terms of p dash y and m. So, p dash y and m will take care of the shape of the ellipse. If you further simplify, you can write p minus p dash y by 2 whole square is equal to q square by m square. What we are doing is we are just multiplying it by p dash y by 2 the whole square. So, that will be equal to p dash y by 2 the whole square. If you expand the previous one, so expand this particular bracket. So, then we will get p dash square minus 2 p dash y by 2 plus p dash y by 2 whole square plus q square by m square equal to p dash y by 2 the whole square. So, this goes on this side and that will become 0. So, we are left with the ellipse equation, which is equal to p dash square minus p dash y plus q square by m square, which is equal to 0. So, this comes from this particular expression. So, this is the equation for elliptical yield curve, and that defines the boundary where the soil is going to yield. So, if you further rearrange this particular expression, we can write m square p dash square plus q square, because we are trying to use these two equations. So, m square p dash square plus q square by m square minus p dash y equal to 0. Now, if we divide it by p dash square, so we can write m square plus q square by p dash square. So, we will get q square by p dash square, where q by p dash is equal to eta. So, then it will become m square plus eta square upon m square minus p dash y upon p dash square will become p dash y upon p dash equal to 0, and the stress ratio eta is equal to q by p dash. Further, we can write the another form of elliptical equation as m square plus eta square by m square is equal to p dash y upon p dash. Why I am discussing all different forms is that you will find these type of forms when you refer to the standard textbooks. So, the equation can be rewritten as p dash upon p dash y, we are just taking the reciprocal, equal to m square upon m square plus eta square. Equation gives a set of elliptical yield curves passing through origin, and what is the kind of the size of the elliptical yield curve is defined by p dash and m. A change in size of the ellipse happens during yielding, because how do you consider the increased size of the ellipse, and that increase in size is completely governed by p dash y, that is when you define p dash in terms of p dash y, and q is equal to eta into p dash. Now, eta into p dash is important because the yield curve goes on increasing and that can go on till failure. Now, when it is at failure, m gets activated. So, that is the final bound, but the concept of yielding keeps on happening, and that will depend upon whether it is hardening or softening. Now, for defining plasticity completely, it is important to determine the plastic deformation. Now, whatever we have done for Camp-Clay model, that is defining of the yield curve, we have done it for MCCM as well. Now, this much we are comfortable with. Now, we will try to add a bit on what happens beyond yielding till failure. So, that is what we will see in this, and that is to determine the plastic deformation. Now, for determining plastic deformation, we need to assume something known as flow rule. how does, it is more like a plastic flow. What happens to the soil behavior during shearing? What kind of flow takes place once the yielding happens? So, that is dictated by some flow rule which we need to assume. How much it is close to the realistic behavior of the soil, that is a different aspect, because for engineers we need to define it mathematically, and for that we need to make certain assumptions. So, flow rule is one such kind of an assumption. Strain in soils, now where does this comes from? Why do we need to assume, why do we need to account for flow rule? It is because strain in soils beyond yielding is divided into elastic and plastic strain. Now, elastic strain is determined based on the concept of linear elastic theory. Plastic strain is determined. Now, the next aspect is how do we determine the plastic strain? Now, this can be determined based on flow rule, what is known as plastic potential, and then what is known as hardening rule. So, we need to have some basics on these aspects, and that is what we will be doing in the further slides. Flow rule represents the plastic strain increment beyond yielding. So, once it yields, how the plastic strain increment happens, which is defined by flow rule. Defining yield curve gives yield function, and that is an ellipse in MCCM, and such an yield function is a logarithmic spiral in Camp-Clay model. Yield function is equated to 0 when soil yields and when the plastic deformation happens. So, once it is made equal to 0, that means that it is close to failure, it has yielded and it is close to failure. Now, yield function less than 0 is what it corresponds to elastic behavior, that is within this yield curve. Whatever is the state of the soil within the yield curve, we know that that is elastic condition, and hence the yield curve function or the function of the yield curve less than 0 is supposed to be elastic behavior, and yield function can never be positive, that is it is up to 0 where it yields. Now, beyond that it is not valid. So, greater than 0 is not possible. Greater than 0 means either that particular yield curve is no longer valid, it goes to the next yield curve and next yield point, or if you are talking in terms of failure, what it means is that there is no soil state beyond that. So, that is why there is no question of yield function greater than 0. It cannot be positive for a given P dash phi. So, that is why it is important for that particular extreme yield point or pre-consolidation pressure, the yield function cannot be greater than 0, but it can expand, and when it expands the earlier yield curve is no longer valid. Now, it is a redefined yield curve, and if it is at a failure state, if the effective stress path is touching the failure line or the critical state line, then there is no question of soil beyond that. So, that forms the boundary. So, now let us see some basics of flow rule, plastic potential and hardening rule. Yielding can occur in isotropic, one dimensional or triaxial compression. So, this notion should be very clear to you that yielding is not meaning failure. So, it can happen in one dimensional compression, isotropic compression where there is no shear stress developed, there also yielding can happen, and it can also happen during shearing. So, yielding is different from failure. Now, this is a general representation of yield point. So, this is V versus ln P dash. So, this is the point at which it yields and there is a substantial change in the V. This we know, this aspect we have already seen. Now, in the case of Q P dash, the yield curve, so you can see that this is the way in which the isotropic compression yielding happens. So, this is the point. The one dimensional compression also can yield, and a triaxial compression in QP dash, that is shearing, can also yield. Now, stress path beyond yield surface. So, it means that the stress path can still move forward, that also we have already seen in our previous lectures. When it moves beyond yield surface means the existing yield surface is no more valid. So, once it crosses, then it is for the new yield curve, then it keeps on extending till it fails. The existing yield surface expands or contracts depending upon whether it is a softening or a hardening behavior. Expansion of yield occurs by hardening, or now this hardening behavior is expressed in terms of isotropic or kinematic hardening. Now, what we understand is that after yielding, if it is expansion of yield curve, that is because of hardening. Now, there are two ways in which the hardening is defined, that means expansion of the yield curve happens. Now, that hardening is defined in terms of either isotropic or kinematic hardening. Now, this is our yield curve, the initial yield curve in general. So, it need not be a critical state or modified Camp-Clay or Camp-Clay, it is a general yield curve. Now, in the case of isotropic hardening, what do you mean by isotropic hardening? It is simply an increase in the size of the yield curve, the one which we have seen till now, and that is what we will be using, because the Camp-Clay model and the modified Camp-Clay model uses the concept of isotropic hardening. Now, what do you mean by isotropic hardening? It is simply the increase in size of the yield curve as the effective stress path crosses beyond the existing yield curve. So, yield surface expands isotropically. Origin of the yield surface is stationary, this point is not going to change. Camp-Clay models, that is both Camp-Clay and modified Camp-Clay models, they are following isotropic hardening. Now, what is meant by kinematic hardening? This is the initial yield curve, and in kinematic hardening what happens is the whole of the yield curve gets shifted. You can see that it no longer follows the initial origin, it is getting translated from its earlier position. So, that is what is meant by kinematic hardening, that is yield surface translates from this particular location to that particular location. It has the same shape and area, that is initial shape and its area is not going to change, it simply it is relocated. It translates in the direction of stress increase or how the stress path moves, no longer at the same origin. So, that is essentially the difference between isotropic hardening and kinematic hardening. Now, what is discussed in this particular course and what is not discussed in this particular course? We understand what is hardening, we understand what is isotropic hardening and kinematic hardening, but we are not going to translate this into an exclusive mathematics for this particular model. So, that is not what is dealt in this particular lecture or in this particular course, and that will be the extension of your learning from taking this as the basics. So, that is about hardening, like what happens to the yield curve beyond it yields. So, now let us see, we also need to define the plastic strain. Now, how do we account for plastic strain, and for that we need to understand what is meant by plastic potential. Now, beyond yielding there will be plastic as well as elastic strain, that is why it is called elastoplastic response. So, elastic strain will also be there and there will be quite a bit of plastic strain as well. Now, we need to define or we need to account or we need to determine these strains, then only our model is complete, and that is where what we are not doing in this particular course. We are yet to define the strain completely, but we will discuss like what we need to have further, and that is both elastic and plastic strain. So, let us take a typical sigma versus epsilon response. This is elastic response, then it yields and there is a bilinear response which is shown here. Sigma dash y is the yield point. and this is a typical hardening behavior. And this is d epsilon, that is beyond the yield what is the total strain that is happening. Now, if I expand this and show here, this is the total strain that is happening beyond yield. This much portion is elastic strain and that is represented by d epsilon E, and the plastic strain is represented by d epsilon P. So, total gives the d epsilon, which is the total strain. D epsilon E is the recoverable elastic strain, epsilon P is irrecoverable plastic strain, and the total elastoplastic strain is the summation of these two. Now, to define this further, I mean to say the strain, we need to make now further assumptions. In modified Kamm-Clay, or rather in Kamm-Clay models, coaxiality is assumed. Now, this is another assumption that we need to have in order to determine the strain. That means, this particular aspect, the plastic strain, that is d epsilon P, it will have components in Q and P dash. That means, the plastic strain due to volumetric behavior or volumetric changes, and plastic strain due to deviatoric changes, and that is represented, and that plastic strain is decomposed into the component due to Q and the component due to P dash, and this is designated as d epsilon Q P and d epsilon P dash P. Now, this is due to the plastic strain due to Q and this is the plastic strain due to P dash. So, this is the typical yield curve. Now, this is what it represents, d epsilon P Q and d epsilon P P dash. So, this is corresponding to P dash and this is corresponding to Q. Now, who has told that this particular increment is in this particular direction? That means, it is in the direction of P dash, this is in the direction of Q. Who has told this? Now, this is represented by how the strain increment vector happens, that is the plastic strain increment vector, which is represented by d epsilon P with a crown. So, this is the plastic strain increment vector. Now, this plastic strain increment vector or its knowledge is quite essential for defining the plastic strain. So, plastic potential followed by plastic strain increment vector, these are two essential elements, but the question remains, who has told that this is in this direction? Now, in coaxiality, that is the assumption of coaxiality, we assume that d epsilon Q P, d epsilon P dash P is in the direction of Q and P dash respectively. Now, that is the importance of coaxiality assumption. That means, whatever is the strain that happens in the direction of stress. So, that is what is meant by coaxiality. Coordinate axes of stress and strain are superposed in coaxiality assumption. You can see that this particular axis and this particular axis, which denotes the plastic strain, is superposed with Q and P dash axis respectively. So, this assumption is what is known as coaxiality. So, when you start learning plastic behavior of soil, or if you want to learn more mathematically, you will come across these terminologies. So, it will be very easy for you to understand further when you know these terminologies. So, the assumption of coaxiality is valid for NCCM models. So, for us, we are discussing this with respect to critical state models. So, let us further go ahead. So, now we have defined yield curve, we have defined coaxiality assumption, and then we have seen the hardening rule, that is isotropic or kinematic. Now, these are some of the elements. So, now we need to move further. Plastic potential is a function that is assumed to exist in stress space. Now, we need to define plastic strain increment vector. Now, for that we also need to define what is known as plastic potential. Now, what is plastic potential? It is a function that is assumed to exist in stress space. Now, what is the beauty of this function? It is a scalar function which, when differentiated with respect to that particular stress, gives plastic strain. Now you understand how do we get plastic strain? It is very essential to define plastic potential, because it is a scalar function, and when you differentiate that particular scalar function with respect to the corresponding stress or with respect to a specified stress, it gives plastic strain corresponding to that particular stress condition. So, define plastic potential and get plastic strain. So, let us say this is a plastic potential contour. This we have already defined. So, d epsilon q and d epsilon p dash p, and this is the plastic strain increment vector. Plastic potential contour describe the direction of plastic strain increment vector. So, very essential to define the plastic potential, so that this is obtained and this is also defined. The change in yield surface is related to plastic volumetric strain, and that is called hardening rule. That we have seen, the expansion of yield curve is in terms of p dash y, and that comes from the hardening behavior, and that comes from the plastic volumetric strain. Defining specific mathematical function for plastic potential is required for determining plastic strain during shearing. So, we need to define or we need to allocate certain function for this plastic potential, then only we will be able to determine plastic strain. Now, this opens up another concept which is very essential in plastic behavior of soil, and that is what is known as associated and non-associated flow rule. How do you define plastic potential? So, there it has something to do with this particular concept which is known as associated and non-associated flow rule. When plastic potential function is considered same as yield function, it is called associated flow rule. Very easy. Like what we are considering is, we have already defined the yield function, which is ellipse or logarithmic spiral or any other shape. What we define is that the plastic potential function is same as the yield function. When you make such an assumption, this is known as associated flow rule. The plastic flow rule is associated with the yield curve. Now, it makes our life very simple, like we need to work with only one function, and remaining things are known, like how to evolve the plastic strain. Of course, I am not discussing that in this particular course, but definition of plastic potential is important. So, we have already done that in the case of associated flow rule. For isotropic material, the axis of principal stresses and principal strain are coincident, that is coaxiality we have already discussed. For associated flow rule, yield function f is same as plastic potential g, and d dou f by dou sigma is in the direction normal to yield curve. So, that is also very important. So, that is how it looks like q versus p dash plastic potential, which is same as the yield curve in the associated flow rule. So, this is yield curve as well as plastic potential, and we have the plastic strain increment vector, and that is normal to the yield curve. So, this is 90 degrees. So, that is normal to yield curve. Now, plastic strain incremental vector is outward normal to yield curve. So, this is outward normal to yield curve. So, such an assumption is called normality rule. What it states, the plastic strain increment vector, this direction is perpendicular to the tangent at this particular point. So, such an increment, that is at 90 degrees, it is outward normal to yield curve, this is called normality rule. So, that is also need to be satisfied, and hence yield curve and plastic potential both are same, as you can see, and this is the stress path, and the plastic strain increment vector is given in this manner. Now, when you define this mathematically, that leads to the determination of plastic strain. So, normality rule may sometimes overestimate the plastic volumetric strain, may not be realistic, that is what it means, but this makes our life simple, that means the mathematical complexity is reduced by such assumption, but always keep in mind there is a possibility that it may overestimate plastic volumetric strain. Now, CAM-clay models, both CAM-clay and modified CAM-clay, obey associated flow rule and normality rule. So, both associated flow rule and normality rule is applicable for these models, and hence our discussion is mostly associated with that. What is meant by non-associated flow rule? When we consider yield function is different from plastic potential, or rather plastic potential G is different from F. So, then we say it is a non-associated flow rule. So, yield curve and the plastic potential, they are different. For simplicity, associated flow rule is mostly preferred. For more realistic behavior, a non-associated flow rule is preferred. Now, further reading on this, now I cannot go beyond this because for this particular course, this is mostly an introductory aspect of plasticity behavior. There has to be an exclusive course on plastic behavior of soil, and for that the readers or the participants are advised to go through this particular reference book and any other reading material on plasticity behavior of soils. Now, some important aspect related to plastic strain increment and with respect to the critical state. Let us say QP dash. Now, stress path to failure is defined. Now, let us say this is the starting point of shearing, this is the critical state line, and we can define the yield curve. The yield curve is small, ESP has not reached the critical state line. Now, at this particular point, if we try to mark the plastic potential or plastic strain increment vector, how it will look like? Now, the plastic strain increment vector is not parallel to Q axis. That means the plastic volumetric strain increment is not 0. I will explain what actually is this. Now, you can see that this is the plastic strain increment vector, the direction at this particular point where the effective stress path is touching the yield curve. Now, this has not failed. Now, at this particular point, the direction of this, that is the plastic strain increment vector, this is not parallel to Q axis. Now, if it is not parallel to Q axis, it means that plastic volumetric strain increment is not 0. Now, what is the implication of this statement? Plastic volumetric strain increment. We will see what is the implication of this statement. This is the plastic strain increment vector. Now, let us say the ESP reaches critical state line. So, this is the condition, and that is defined by the yield curve or the elliptical yield curve. Now, at this particular point, what happens is you cannot further increase the yield curve. Now, we have seen in the previous slide that increment of the yield curve is dictated by the plastic volumetric increment, strain increment, that is this one. Now, once it has reached the critical state line, soil has failed. There is no more question of existence of the soil beyond that. That means the plastic volumetric strain increment cannot happen beyond this. From here it is possible. The plastic volumetric strain increment happens as the effective stress path moves further, but once it reaches this, there is no more, it has failed. There is no more soil beyond that particular point. So, the plastic volumetric strain increment becomes 0 at this particular point, and when that becomes 0, that is d of epsilon p dash p, that becomes 0 means it has to be parallel. That means this plastic strain increment vector, it has to be parallel. That is, yield curve meets the point of intersection, that is what I told, and 0 gradient at this point on the yield curve. What is meant by 0 gradient? At this particular point it is 0 gradient, that is at the point where it, so here the slope is 0. And the plastic strain increment vector is parallel to Q axis. Now, this is the situation where only del d of epsilon q p exists, d of epsilon p dash p, it does not exist. That means plastic volumetric strain increment is 0, only plastic shear increment happens indefinitely. Now, this is indefinite. Now, we kept on telling this right from the day 1 when we started discussing critical state. At critical state, the soil shears indefinitely. Now, you will clearly appreciate what is meant by the statement in this particular slide. Like this plastic strain increment vector in the q direction means it is shearing indefinitely, it is infinite, whereas d epsilon p dash p, which shows the plastic volumetric strain increment, that becomes 0, and there is no further change in stress because soil does not exist beyond this point. So, two conditions are satisfied when the effective stress path reaches the critical state line and for the yield curve which is defined by this. So, here d epsilon p dash p is equal to 0, and that is exactly what is meant by this condition. Now, for this particular plastic strain increment vector, there is d epsilon p dash p, that is possible, that is why it is expanding, but at this point it stops, it becomes 0, and that is the condition where this plastic strain increment vector is parallel to q. No further volumetric change. So, there are two things which are satisfied here, and no hardening possible, soil reach ultimate state of failure and no change in stress. So, no volumetric change and no change in stress, but shears indefinitely. So, this particular figure shows exactly what is happening at critical state. Now, if you want to understand this, we need to understand the basics of plasticity behavior, what we just discussed. So, that is all about MCCM and some basic elements of plastic behavior, which is very important. And now, let us try to summarize what we have learned in this lecture. MCCM is a popular elastoplastic model that can incorporate hardening, softening during shearing. In MCCM, the shape of the yield curve is ellipse, but we have talked about hardening only. It is basically an isotropic hardening model. So, in MCCM, the shape of the yield curve is ellipse and it is logarithmic spiral in CCM. It may not be applicable for all soil type, as I told, when we do a mathematical modeling or mathematical definition, we cannot make it generalized. So, there will be some cases where it may not apply. For ellipse, the ratio of major to minor axis is considered as the shape parameter, how it accounts for further expansion. The essential elements needed for elastoplastic models are elasticity, yield, criteria, plastic potential, hardening rule. All of them, the basic definition and what it actually means we have discussed. Flow rule represents plastic strain increment beyond yielding. Cam clay models follow isotropic hardening. So, we have these are basically hardening models. In MCCM or cam clay models, it follows coaxiality, which is important for defining the plastic strain increment vector. Plastic potential is a function defined for determining plastic strain. In critical state models, plastic potential function is taken equal to yield function, which is known as associated flow rule. So, plastic strain increment vector is outward normal to yield curve, which is normality rule. For more realistic soil behavior, a non-associated flow rule is preferred. The slope of yield curve is 0. Please understand under what condition? Where it meets the point of intersection of ESP with critical state line, and that is why at that particular point the plastic strain increment vector is in the upward direction. Plastic strain increment vector is parallel to q axis at this particular point. At this point, plastic volumetric strain increment is 0, indefinite shearing happens at constant volume and stress. The application of CCM and MCCM requires the definition of complete stress strain constitutive relationship. Now, this course does not deal with the determination of elastic and plastic strain. We have defined the basic elements of plasticity behavior, but the complete constitutive relationship beyond the yielding we have not defined. That means, the plastic strain we are not actually determining in this particular course. Okay, so that is all for the critical state models. Now, we will see a bit about prediction of critical state behavior in the next lecture. So, that is all for now. Thank you.